Okay, so for this problem, it's going to begin like the other two problems, which is we first solve the homogeneous equation. So once again, we've got our y double prime minus 3y prime plus 2y is equal to 0. And it's got solutions y1 of t is e to the t, and y2 of t is equal to e to the 2t. And now we'll notice for the first time that we have linear dependence of our forcing term and these two solutions of the homogeneous equation. In fact, you will notice that if we take 0 times e to the 5t plus 5 times e to the 2t, we will in fact get 5 times e to the 2t. So we can express this as a linear combination of those two. So once again, to break linear dependence, we put a t in front of our exponential function. So our particular solution is yp of t is an unknown constant a times t e to the 2 times t. And then just like before, we need to go take the first and second derivatives and substitute them into the inhomogeneous equation. So we take our first derivative. We'll notice right away that the calculus gets a little bit more challenging because we have to use the product rule. Derivative of the first is a times e to the 2t plus at times the derivative of the second, 2e to the 2t. And I highly recommend cleaning up these derivatives before you go through and take higher derivatives. So cleaning this up, we actually have 2at plus another a e to the 2 times t by combining like terms and factoring. We now take the second derivative. So derivative of the first is 2a times the second plus the first times the derivative of the second. Once again, we will combine like terms. This time around, you'll notice that we've got a 2 that's hitting the 2at. So that's going to make a 4at. And then we have that 2a getting together with the other 2a to make a total of 4a. So that's plus 4a all times e to the 2t. We can now substitute that second derivative and first derivative and original function into our inhomogeneous differential equation. So in place of the y double prime, we will have our 4at plus 4a all times e to the 2t. And then our differential equation has minus 3, and that's times the first derivative, which was 2at plus a e to the 2t. And then we have a plus 2 in our differential equation times the y, which again is at e to the 2t. And this must all equal out to our forcing term, which is 5e to the 2t. When you multiply this out, we'll first look at all the coefficients. We'll have a 4at plus 4a, then a minus 6at minus 3a, and then a plus 2at. And again, this is all multiplied times the e to the 2t, and that must equal 5e to the 2t. You will notice that when you do this comparison, you will always have, and I use the word always strongly here, the at terms canceling out. We've got 4 plus 2 makes 6, minus 6 makes them cancel out. And that has to happen in this process. If it doesn't happen, that means there's a mistake that was made in this calculation. But again, you will notice here that they do cancel out, and again, that must happen every single time. So what's left on the left side is just 4a minus 3a. That leaves just one single a, e to the 2t, and again, that's equal to 5e to the 2t. We now compare those coefficients, and we see that a must be equal to 5. So that is our coefficient on our forcing term. So our particular solution, yp of t, is 5 times t e to the 2t. And therefore our general solution is y of t is c1 e to the t plus c2 e to the 2t plus 5t e to the 2t. And just like before, you will notice that these three terms are linearly independent, and therefore we have our solution of our inhomogeneous equation.